So here we are. I've made a few modifications, and one of the things I wanted to show you is that we don't have to just add or subtract numbers. We can also act on other variables. So here I've written a line that C is equal to A plus B. Let's compile that and see what the results are. We're at it. I'm going to clear this page and wait for it to finish. Okay, it's done. So let's see what our result is. 7, 3, and the sum 10, just as we expect. Now, the next thing I want to show you is that it's possible to give our variables initial values. So here I am doing A is 10 and B is 5, and I'm going to get rid of these two lines. So now we expect that when we add it together we should get 15. Clear the screen so that when we're ready. There we go. So let's see, we get again 10, 5, and 15 as expected. Great. Now there's a couple of little shortcuts that are not what we normally do in terms of math operations. Here's one of them. A plus plus semicolon. This operation says A equals A plus 1. Okay. That's very common in C. B minus minus, as you might guess, is B equals B minus 1. And you could do something as well as, like, say, C times equals 2. And this is C equal to C times 2. Let's build those and see what we get. While we're waiting here, usually you define your variables at the start of the main project, just to keep things from being uncluttered and easy to find. So we've succeeded. So let's go over here and now let's run the program. And A plus plus, well, we had 10, we add 1, right? B minus minus is 5 minus 1 is 4. And C times equals 2, well, C was 15, and we've multiplied it by 2. We also, on our calculator, have special functions like square root, sine, cos, tan, powers that we'd like to be able to use. Now, they're not part of the XC8 compiler lowest level, but they're included in a directory called math.h. If you want to see what functions are available, at the back of our course notes, there's the library, I said, that tells us how to make use of these functions. Now, what we're going to be looking at are not integers, but we'll call them like float, A, B, C, and D. And some of the functions would be things like A equals the square root of 4.0. We might look at the sign of a number, say 0.1. Remember, sign uses radians. C could be things like the power function, like power 5 to the 3. Okay? So that takes 5 and raises it to the power of 3. And finally, for D, well, how about the log of 100? And let's change these all to floating points. Float, 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 percent %f. And let's see what happens when I build them, see if I have any mistakes. Oh, I am so bad typing. So let's fix that here. Okay, and let's see if that's everything. Oh, I still have an error here. Okay. So here we are again. I fixed the typo. I had an extra bracket down here that I didn't need. So I've got all this, and you'll notice I've shrunk the screen size to save a little space. I'm going to compile this and see what happens. Again, very slow for these to build. It's kind of annoying. And sorry for the waste of time in the video. You can always skip a little ahead, of course, when we're in the builds. Okay, we are done. So we want to go to the UART window, and in the UART window, we want to run the program. And a couple of things you'll notice here. First of all, the numbers are all printing out. That's great. Let's look at those numbers first. The first one is the square root of 4 is 2.000061. That's the first thing to notice. These numbers aren't what we would get on a calculator, partly because of the size of the floats. Here there are about 24 bits, and so what we're seeing is the sort of uncertainties in these measurements. So you have to be kind of careful with that. They don't give you as many digits as you would like. The second thing here is it keeps repeating itself. It hadn't repeated itself before because we had used to put a breakpoint right here, but I didn't do it this time. Now it's part of the nature of these PIC-MCU programs. They're supposed to be put in machines. So if the machines accidentally shut off, when they get power again, they restart. So our functions don't typically end. Once they come to the end of the program, they start over again. And so what we're seeing here is the program restarting over and over and over again. If I let them run, it'll keep running for a fairly long time. And then we're going to get this message. There's a built-in part of the PIC called a watchdog timer that looks for infinite loops, loops that are continuing too long. And this is just saying, is this an infinite loop? Do you want me to stop? We don't worry about this. We can let it appear again. But what we're going to do is we're going to get rid of that behavior where it always appears to be ending and restarting. And the way we do that is we put in what's called a while one loop. While one plus a semicolon is a statement that while what's inside is true, and true is 1, the number 1 holds the status of being true, 0 is false. So while this is true, it just waits and waits and waits. A while loop is essentially the same as wait forever. Let's build this and see the difference between the two runs. Still waiting here. Finally. So let's go to the UART window. Let's clear it up and then run the program. Now it only happens once. We can, it's still this watch timer occurs because that's an infinite loop. Do we want this warning to appear again? No, we don't. So we'll run it one more time. Right? And it will, right, none of the warning message, just that this watchdog timer occurred. I'm going to talk about this later. Don't worry about it now. Let's stop right there. So here we are. One of the things we've discovered is that our numbers don't round as to values that we're happy with, and that's because of the size of the floats. Where we change the size of the floats is we go to Build Options, Project, and in Project we go to Global. And what I've done is you can switch these between being fairly small and relatively inaccurate numbers to fairly larger numbers, 32-bit. So when I apply that and build again, and wait, and wait, and wait, any moment now. Okay, there we are. So let's go to UART window and run this. Okay, now the numbers, again, that watchdog timer timed out, not a problem. I'll show you how to fix that later. Now you can see that the number, the square root of 4, is to significant better decimal places. You might notice up here that I also have the right numbers because I was playing with this before I recorded this video. So what we want to do, we always want to make sure that we set the project to 32 bits. It might be for you, when you do your project, go to global here, you might already find it set to 32. What I found was a bit of a bug. I had to send it back to 24, compile it, run it, then go back and switch it to 32, and then I got the correct numbers. So it's a little buggy. So if yours are already set to 32, go back both of them to 24, say apply, okay, build the project, wait forever, Still waiting. There we are. And now we run. And you see it's back to the 24-bit, right? So what we're going to do, we're going to go to the project, build options, project again, the global, set them to 32 bits, right? So if the values don't look right and you go here and global was set to 32 already, reset to 24, apply, rebuild, then go back to 32. Apply, OK, rebuild. OK, and so from here, and we run. We're back to the correct number of digits, or much better digits. All right, we'll end it there.